Okay. Yes, first of all, I would like to thank the organizers for the invitation. Secondly, I changed the title of my talk. So initially I wanted to talk about exact solvability in classical cellular automata. If you want to know more about that, you can of course talk to me, but I also just flashed the latest reference where basically we develop unifying algebraic approach with which you can basically solve, at least in this case, inhomogeneous quench in terms of matrix product ansatz, or like localized initial excitation or driven system, and everything is based on the same framework. Okay, so sorry. Yeah, sorry. Okay, so I will talk about a bit more controversial issue, which is quantum time crystal. In particular, I'll focus on isolated Heisenberg model. Okay, probably you heard about quantum time crystals, but let me just initially flash through the kind of the most important concepts which underlie our understanding of thermalization in isolated quantum models. So why do we think that many-body quantum systems equilibrate? Even if they don't thermalize, as we all know, if they are integrable, they are still expected to reach some stationary ensembles. So the first notion is called eigenstate thermalization hypothesis, which states that off-diagonal elements of local observables in the eigenbasis of local Hamiltonians vanish if their energy densities differ exponentially with the system size. The second claim is that diagonal elements are smooth functions of energy. Of course, if we have more conservation laws, this can be straightforwardly generalized. So in integrable systems, we have something called generalized eigenstate thermalization hypothesis, which states that we should fix all local conservation laws. The second notion, which is important, especially in this case, since I'll be talking about integrable model, is the GGE hypothesis, which states that if you prepare a system in some initial state and wait for a long enough time, basically in the large time limit, the expectation values of local observables will be described by generalized thermal ensemble, which depends not only on energy, but also on other local or quasi-local charges, so charges that are extensive. Why only extensive charges? Because entropy is extensive, and in maximization procedure, if you would want to add quadratically extensive charge, the corresponding chemical potential would just decay with the system size. Okay, so the third notion which I'll use and has been used extensively, for instance, in this Drude-Wade business, is the notion of hydrodynamical projection, or as the name mentioned, a related concept of Mazur lower bounds and dynamical susceptibilities. This tells us that basically if we're looking at local extensive observable and calculating dynamical susceptibilities, so this is just a connected correlator of extensive observable OK and OL, where OK is propagated in time. with respect, for instance, to some thermal state, can be obtained in infinite time limit simply by projecting on the basis of quasi-local charges. And the reason for that is quite simple. So, well, it's not like really formal or rigorous, but if you take this observable, take time to infinity, it will be conserved, because if you propagate it a bit more, it doesn't matter. Time is already at infinity. If it equilibrates. If it doesn't, then we don't know. And the second property is that time evolution with local Hamiltonians preserves the locality of observables, at least for finite times. So you can see this is not really rigorous. These are just some arguments which tell us that time-propagated observables, at least in some sense, if they are local, in infinite time limit, relax to some conserved quasi-local observables, and you can then just project them on the complete set of quasi-local observables. Okay. So let me move to the title of my talk, which is quantum time crystals. So this area was very controversial. So in 2012, Wilczek proposed quantum time crystals in PRL, and kind of his intuition, okay, he solved some model approximately at the ground state. Kind of his intuition was that, for instance, if you look at superconductors, you have persistent currents, so something is always moving. But of course, as he noticed, this shouldn't cause oscillations because currents are constant in time, so it's just moving with constant velocity. But he went further and said, okay, but what could happen is that due to some kind of interaction, systems could, like particles could start clustering together, forming, in some sense, some kind of solitons, if you want. I mean, solitons. And then, like, these packages would travel around the system. And this, he envisioned that this could happen in the ground state, so at zero energy. Why was this so controversial, and why did he like this idea so much? Is because then you would have motion at zero energy. So without any energy, you would have some kind of motion of some particles. So you can see that kind of intuition and descriptions are very fuzzy. And of course, people were bothered by his proposals, and basically there were a couple of comments on paper which culminated in the no-go theorem of quantum time crystals. So yeah, as you can see, so in 2012, there was an article in PRL titled Quantum Time Crystals, and in 2015, the name of the article was Absence of Quantum Time Crystals. So yeah, it is a bit confusing, and one can see why people are a bit skeptical about these studies. But okay, after the no-go theorem, people said, okay, but let's try to still get somehow time translation symmetry breaking. And then they started studying driven systems, so Floquet systems, and then they said, okay, so we have discrete time symmetry, but what can happen is that discrete time symmetry can get broken. And they actually did theoretical studies of that and even experimental realizations of time crystals. Then there were also some studies studying time crystalline behavior in open systems. But there is also kind of funny sentence in Wikipedia talking about time crystals, which says this state of matter cannot be isolated from its environment. Citation needed. Is an open system in non-equilibrium. Okay. Good. So let me just, well, provoke you a bit, especially with this data. So I take Heisenberg model. I put delta to -1/2. I put h to, well, 1 or 2. Doesn't really matter. I initialize my system in a state which is polarized in x direction. And then I use the MRG to compute 2 observables. One is 3-point correlation function. This is Hermitian observable. And the other one is just magnetic field in x direction. Of course, if I put delta to -1/2, I have no SU2 symmetry, so you expect this to relax. And indeed, we can see the red curve nicely relaxes to 0. But what's happening with this guy is, well, it kind of seems that it keeps on oscillating. Does anyone have any problems with The blue one is 3-particle. Okay, I hope you don't believe me at this point that this is a quantum time crystal. So let's ask then a question. Okay, so we see some, okay, this is not really well seen, but yeah, okay, I cannot correct it now. So we can see some oscillatory behavior. We don't know if it's stable, but let's look at the definition by Watanabe, who, well, with collaborators, proved the no-go theorem. Okay, I really have to tell you what is here. So he says the following. Take an observable, which is an extensive observable. So he takes some local field, and he integrates it over the space. And then he computes the susceptibility of time-dependent field with field at time 0 in either ground state or thermal state. And then he divides the susceptibility with volume squared. This is important. And using Lieb-Robinson theorem, he proves that this guy has to relax. It cannot have some oscillatory behavior. But now, actually, we don't need to use Lieb-Robinson theorem to see that in one dimension at non-zero temperature, this actually vanishes. So because we divide by 1 over volume squared, and this is an extensive observable, this is the connect. So because it's a connected correlator, it's a thermal state which is clustering, so exponentially clustering. If you take 2 local observables, take them far apart, the contributions will vanish exponentially. So even if you take time here equal to 0, because you are dividing by volume squared, this guy is proportional to volume, this will vanish as you take volume to infinity. So actually it doesn't tell us that much, this definition about one-dimensional systems. Yes, sure, but there you can have phase transition, and why he defines it like that, he said, I mean, it makes sense, because, I mean, he demands long-range order. And of course, if you have a space crystal, you'll have a long-range order. So, I mean, you can imagine, so what's a crystal? So you have particle here, particle here, particle here. And even if you go like really far apart, they will still be correlated. And this will scale as volume squared. So basically, because we don't have crystals, strictly speaking, in one dimension, we don't have time crystals in one dimension. But we also don't have spin chains, so yeah. Okay, but yeah, okay, we don't want to throw away one-dimensional systems. So let's try to make some definition which will tell us whether systems will equilibrate or not. So the first definition is the following. So you can take some local observable, but here I should stress that this should be many-body observable. And you take some initial state, which is not some simple state composed of a couple of eigenstates, but well, some generic enough state. And if the behavior of observable is periodic, so, okay, I think you all understand this, then we call this time crystalline behavior. So this observable will never relax. But importantly, we also demand a single body observable to relax, because we want to exclude one body phenomena, if you want, spin precession and things like that. So with demanding that this observable should be a many-body observable, we basically are probing many-body physics. And of course, that one-body observable decays, because many-body observable could also depend on this one-body observable, but this is trivial. Okay, the second definition is really similar to this one, just that we normalize it at time 0 and demand that this function is time-dependent. Okay, so I'll now connect the notion of time crystal as I defined it to periodic extensive quantities, or quasi-local quantities, if you want. So instead of these quantities being conserved, when you commute them by Hamiltonian, they're actually an eigen operator. So they satisfy this closure or eigen operator condition. And if this is the case, of course, time evolution of such quantities is simple, trivial, if you want. And then we ask ourselves, what if we have such quantities present in a system, how can we describe large time behavior if we start from some initial state? And secondly, how can we describe dynamical susceptibilities after a long time? So these are basically two defining properties of time crystals as I introduced them. Okay, so this is not very rigorous, I should say that, and this is a conjecture which should be checked, but no, it's not Hermitian exactly. Y dagger has the opposite frequency. No, it's not an it's neither Hermitian nor anti-Hermitian. It's so if you have Y which satisfies this property, you also have Y dagger which satisfies this property with the minus sign here. Just put dagger on this relation. Yeah? Some more questions? No. I'll show you. So okay, but a good comment. I mean, this. I mean, you also, if you have y, you also have y dagger with the opposite, with the time evolution, which is opposite in time. So okay, if we have like time-dependent periodic quasi-local observables, we can define a map which basically renders the periodic quasi-local observables. Okay, that this name is too long. Conserved, because you just basically look stroboscopically at what happens. Let's say that all such observables have the same frequency, since this is exactly what will happen in the considered example. Then we expect the steady state in the long time limit to reach time-dependent GG distributions. There are some subtleties here, because it will turn out that y and y dagger do not commute. Sorry? Omega is just number which corresponds to this. Let's say that we have just observables with one frequency. Right. Yeah, thank you. Yes, indeed. Yeah, there should be Hamiltonian here. Okay. Okay. This should not be here. Yeah, sorry, I was preparing slides a bit late. But okay, what do we depend from this TGG? So things are actually a bit subtle, and it's, well, okay. Let me just present a simple picture. Yeah. Yes. It's an extensive. Yeah. 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 Exactly. Yeah. Yeah. But if you just so we demand, so we want to probe many body dynamics. So like because sorry. Yeah, yeah, yeah. I mean, we understand precession, right? Sorry? Okay. So additionally, first of all, these time-dependent GGs should reproduce dynamics of quasi-local charges, time-dependent, which under certain conditions on these charges can be satisfied by time-dependent chemical potentials. And secondly, of course, conserved quantities should also be the same in these GG ensembles. Yeah, yeah, sure. What do you mean? Which part? If what? Yeah, that's a good question. So, I mean, in the end, I think what actually happens is that everything can be reduced to the rotating frame, but which is not equal if you introduce just magnetic field, because these quantities have some strange properties. This is not rigorous, as I said. This is okay. Okay. So the second thing is hydrodynamical projection. I can project now, take into account conserved quasi-local quantities and periodic ones, and then I get this time dependence. Okay, So how do we get such quantities in a concrete model? Well, we look at the paper from 2016, which where with Lennart and Tomáš we constructed so-called semi-cyclic representations, semi-cyclic quasi-local conservation laws, which originate from the semi-cyclic representations of UQSL2, which look like this, okay. So what are their properties? They break the U1 symmetry, so they don't commute with magnetization. They don't commute even with each other. Y dagger doesn't commute, sorry. Y commutes, so Y commutes for different values of lambda, but Y and Y dagger do not commute. So somehow, even if you, okay. And they are not conserved if you have finite magnetic field in your Hamiltonian, but rather they satisfy this closure condition. So what are some other properties of these charges? The densities of these charges have a surplus of sigma plus or sigma minus operators, where the surplus corresponds exactly is directly connected to the anisotropy. And these quantities exist only for roots of unities. So when in the easy axis plane, okay, thanks. In the easy plane regime. But they are even weirder because they don't exist for all the roots of unities. So I'll comment on that later on. Okay, so now let's look at some numerics. As we can see, for this three-site observable, as I showed you, the system doesn't equilibrate. And for a single-site observable, the system equilibrates. It seems that the behavior is even stable under perturbation of delta, because the three-site observable will oscillate just at delta equal minus 1/2. This is the only point, even not at delta 1/2, despite the fact that there is unitary transformation which connects the two. But if we go a bit away from delta, the time evolution is really similar. Okay. So let us now turn our attention to this hydrodynamical projection and trying to obtain time dependence of dynamical susceptibilities for large times. So we take some observable. We have in Heisenberg XXZ in easy plane regime, we have three different families of charges, Z of lambda, X of lambda, and these Y charges. But these guys preserve magnetization. But if you look at this observable, none of its densities preserve magnetization, so traces are automatically 0. So we can forget about these charges. Then we can again use the hydrodynamical projection, and basically we get a constant times some cosine term, and constant from knowing the properties of overlaps of the charges with observables, with these observables, and basically overlaps of charges amongst themselves. We can compute the constant in front of cosine. Okay, this constant is can be obtained by multiplying some simple matrices and evaluating some matrix element. But I'm pretty sure we can also find an analytical expression for this. For instance, if we take K3, L3, and M3, so M3 will correspond to delta minus 1/2. So this is the thing we saw before. K and L3 correspond to basically 3 consecutive sigma x's. So these observables are 3 consecutive sigma x's, which we translate around the chain. And okay, then we can obtain this constant analytically. And now this is backwards. And compare it to numerics. So for single point observable, the expectation value decays. Sorry, there should be another row here and here at 0. So this is autocorrelation function, dynamical susceptibility. For 3-point observable, sigma x, sigma x, sigma x, we see persistent oscillations, which we can compare with result from here, and we see that the matching is perfect. And then, okay, what we can do is also look at delta equal to 1/2. And remember that there is unitary transformation connecting these two deltas. So if we have h of delta is u h of minus delta u minus 1, and u is just sigma z on every other side, if you want. So if we have some conservation loss at delta, we also have, so let's say that y h delta is 0. Then we have, of course, uy u minus 1 h of minus delta is 0. But the point is that at least for observable which will contribute to this correlation function, the observable, this part of y will be staggered. So on site 1, it will be with contribution plus, then it will be with contribution minus, plus minus, which eventually cancels out. So that's why it relaxes. And again, we can see that even we move delta by just a little bit, well, by 0.5, even on large time scales, well, it's not that large, but on accessible time scales, the oscillations are still quite large. So the time scales on which it should relax are quite big, probably. Yeah, okay. So, yeah. Yeah. No, it doesn't. This is just finite time, of course. Yeah, exactly. So under small change of delta, well, the things do not change very much. Okay, what we can look then is how frequencies of oscillations depend on delta, of oscillations of discharges, and you can see that, of course, we again have fractal structure. We could even call it Procéen fractal, right? So, as I said, it's connected to this parameterization of delta. So we had m equal to 3, and if L was 2, this was, these two shouldn't be here. This was delta minus 1/2. If L was 1, it was delta 1/2. So this should be an even number, and m should be an odd number in order for fundamental commutation relations to hold. But of course, as I said, if you do this transformation of the charges, you can symmetrize this diagram, but then you'll see oscillations in some different observables, and they will even not be translationally invariant. Okay, just an outlook. So what's missing is the string charge interpretations of these charges. So which should be expanded. Better understanding of non-commutative GGs. So as far as I know, there are two works on non-commutative GGs, one by Maurizio Fagotti and the other one by Benjamin. So, okay, this is more formal about the existence. And here, Fagotti actually considers GGs in free systems which have non-commutative charges. And what he concludes is that there exists a set, so if you take a steady state, sorry, not a steady state, an initial state will basically decide on which combinations of all charges will describe your long-time GGE. And this set of charges commutes. So you have large set of charges which do not commute. And what Maurizio sees for free systems is that if you take a steady state, you should just take some subset of charges, appropriate linear combinations, so that they commute. And this defines your, if you want, abelian GG. And then he also studies like time-dependent GGs. But in his case, this eigenoperator condition is not satisfied. So in his case, charges produce more other charges, which destroys this periodicity. But in like asymptotic behavior is still well described by the time-dependent GG, where he just evaluates the time evolution of the charges in the GG. Okay, so the third question is whether there is a classical analog to what I was describing, and of course there was a lot of people were talking about Landau-Lifshitz model, and of course the first model where one could check it is anisotropic lattice Landau-Lifshitz. Then the second question is whether there could be quantum phenomena basically on really large time scales. Effectively, can you measure commutators of some quantities? And finally, it would be nice if one could unify all of the non-relaxing systems. And for instance, for quantum scars, they already observed, if I understood correctly, approximately constructed the types of charges that I was describing on some reduced subspace, because quantum scars are properties of some like zero measure subspace of the whole Hilbert space. Then, as I said, time crystals or time translation symmetry breaking was observed in driven system and open system. So the question is, can one relate it to the types of charges that I described? Okay, so with this I thank you.
Thank you, Marko, for this nice talk. We have time for questions.